So I think that it's no secret that Enrico Bombieri played a central role in recruiting Jean Bourgain to the Institute, a move that I think has worked out extremely well for the Institute and also for Jean. Given Enrico's foundational and far-reaching works that have shaped most aspects of modern analytic number theory as well as Diophantine geometry, it was inevitable that he and Jean would work together on some problems. It is a pleasure to introduce Enrico to talk to us about exactly this, working with Jean Bourgain.
So, I've been lucky enough to be able to work with Bourgain. Now, my mathematical preparation is very, very classical, almost old-fashioned. And Bourgain's preparation is much more modern than mine, but he knows very well the classical, old-fashioned mathematics. So we could talk together and share interest in some problems. And working on a problem for Bourgain, he never asks, is it important? If he likes it, okay, let's spend some time on it. And I really like this attitude because it also is close to mine, at least when I started doing mathematics. And I've written 4 papers, published papers with Bourgain, and 1 unpublished paper. And I will give you the story of those papers, and of course some comments, how they came up. So the first paper, let's see if I can enlarge it. I will enlarge a little bit to make it a little more visible. Came up when, in the year 2002, I noticed an article in the Proceedings of the London Mathematical Society, in which there was a paper by 3 authors studying a problem about norms of power series. And the problem initiated with the work of Harald Bohr in 1909. If you take an analytic function in the unit disk bounded by 1, it's a very interesting class actually, and you look at the power series its majorant, the majorant is obtained by taking the absolute values of the coefficients. Bohr proved that there is a radius independent of the function, of course less than 1, for which the majorant power series is still bounded by 1. This result was then improved later by Landau and others, and the best radius turns out to be 1/3. Now, this was a cute theorem at the time, but it turns out to be results of this type occur in the study of Banach spaces, and so people working in that area have done quite a bit of extensions, multidimensional extensions, other spaces, and basically because you get an L infinity norm majorized by by what will be an L2 norm, because the function is actually bounded. So it turns out that some of the questions, not of the extensions, but the questions about the original problem of Bohr, was also, instead of saying the majorant bounded by 1, if you say the majorant is bounded by 10, what is the radius? Things of that type. And there were some inequalities about the radius is not more than something, has to be at least something else, but the result by Bohr remained the only exact bound obtained. Now, in 1962, I wrote a little paper in which I obtained the exact bound when the radius was from 1/3 up to 1 over square root of 2. So I was a little disappointed that my little paper, the paper is just a few pages, was not known at all. So I wrote a terse letter to the authors, to the leading author. So it says, "Dear Professor," I don't put a name, but I came across your interesting paper, Y and Z on Bourg's inequality, and then continue. In 1962, I wrote a little paper. This paper is published in a foreign language in an obscure journal. So I summarize it briefly here in the hope you can find it useful. So let's see if I can make it a little larger. Yeah. Good. And let's move up. So the theorem is the following. You have the majorant, you have the power series bounded by 1. And the theorem is about the bound sigma for the majorant and a radius b lambda sigma. Lambda is the leading coefficient, in fact. And the theorem, the first theorem tells you if sigma is between lambda and 2 lambda, we have the exact value of the radius. Then b of sigma is, forget about lambda, you just take the smallest value, and then it turns out that the radius is 1 over 3 sigma minus 2 square root 2 sigma squared minus 1. So that's an exact value, and in terms of the radius rather than the bound for the majorant is the corollary. Okay, so that was. Then I complain a bit with Jean, the fact that people don't look anymore at the literature, and he said, maybe one can do something more. So we started looking what happens when the radius is greater than 1 over square root of 2. Well, we could not find the exact value for any radius greater than that. And if the radius goes to 1, then there is a very trivial bound, which was rediscovered in the paper of 2002. It goes back to Landau in 1910. So here it is. Let's see. And then that. Yeah. So I'll give you the proof just to. The bound is 1 over square root divided 1 minus r squared. It's obtained very simply by Bohrs Inequality. So the proof, because I think it's cute, I will give very quickly, is the first lemma tells you if you have a function in a unit disk, you have a 0 smallest modulus, then you have a lower bound for that. It's a very easy application of Jensen's theorem. The second lemma is the lower bound for this radius. And this is done in 2 parts. One is to notice that the bound, because the series has positive coefficient, is just the value. If you take the majorant and call C the critical value for that radius, then the majorant minus C has a 0 exactly at that radius. So you apply lemma 1, and that's fine, but so there is one condition that you should not go beyond. So you get a result, you have to allow for the minimum of the radius and that. So that's very easy. And then you have to compare the, if you fix the first coefficient, then the square mean value changes. I mean, you can get a better bound with respect to the trivial bound. And this is simple application of Schwarz lemma. If you combine these things, you get what you want. So that was the end of my letter. So this gave rise to a paper with Bourgain called a Remark on Bohrs Inequality. And it turns out to be relatively easy, but then we could not get any exact thing in between, so we shifted to look at the behavior when you go toward 1. And so the first thing is here. Theorem 1. The bound 1 over square root minus r squared is not sharp for any r greater than 1 over square root 2. That was open, and the proof is quite easy, so let's move on. Okay, that's the proof. Orlando, don't care. Let's move on. Okay. So, how to do that? The idea is to look at a bounded function g with coefficients, say, r to the n, because then the majorant is what you want, and try to make this function g as small as possible by adjusting the arguments. So the arguments will be described by using Poisson summation. You get, say, you have to adjust the phases with a function phi of n plus theta n, say. And then you want to compute the value of g and try to make it less than or equal 1. So how do you do that? Well, the first idea was r goes to 1. Let's think the case of polynomials. Then you know Gauss sums, and then you think the phase is quadratic in n. So Jean gave me the task to check that, and simply I could not get anything really good. And so I complained to Jean, oh, does not work. So he looked at what I had computed, and he said, well, of course. You see, with that phase, you get 2 stationary points. So those 2 stationary points interfere with each other, and you cannot have the bounds you want. You need only a phase with 1 stationary point. So he thought for 30 seconds, and he did the following calculation. So you need the stationary phase depends on the second derivative, right? So to get the correct thing, the second derivative should be constant times r to the power 2x of k. Xk is the point of stationary phase. The constant determined the first derivative is 0 of phi has to be 1. And suddenly you have the function, which is exponential in the variable x. It's the first time I encountered that in my life. I thought that was kind of monster nobody is interested in. So then it remained to compute the stationary phase with carefully. And again, he came to the rescue. I just show. He gave a proof. I was struggling a bit, and he came. Was late at night. He said, "Oh, very easy. You take an outer function, which is written here, multiply the function you want by that, and it comes out. And so the error term will be 1 over the 4th root. This is fine, so I started saying, writing it up. Okay, so I started writing it up, and I was not happy that I brought no contribution. So I look a little further, and the point is, let's go, simply that there are, in the Poisson expansion, there are two terms, only 2 terms. The first term is fine, the error term is small. The second, the error term was big, and the stationary phase calculation we did, actually in this particular case, could be improved to get a better error term. So the trick was to compute the stationary phase to arbitrary order, which is the first time I found in my life. But the result was, instead of going like 1 minus r to the power minus a quarter, we got a logger of 1 over 1 to the power 3 halves plus epsilon. So that was the first thing. It was published, and I was very happy with that. The second one is the unpublished paper, which is about linear combinations of the integral part when f of t is bounded for all x. So of course the sum of ck times nu k has to be 0. This arises in study of ratios of factorials with an integral. And for example, Chebyshev used such things to study distribution of prime numbers, as it gave the first correct order of magnitude for primes, proofs at least. And so this will be of some interest. And Borisov made a conjecture which is stated there. And well, I mentioned that to Bourgain, and again, next day, he had a very neat proof of Theorem 1. Just that involves introducing these additional parameters, but he gave a bound for C. Notice you don't take the floor function, but rather the bracket function, which is floor function minus a half, renormalizing things. Okay. So, as a result, the bound is a times log a squared. The proofs, typical of Bourgain, involve, well, first, Cauchy inequality, which he knows very, very well, when to use and when not to use it. That is not enough, so Minkowski's inequality. But it gets trickier, as you can see. Then Cauchy inequality again, and then he got a result. He had this choice for parameters, and I thought, I think Selbers here is better. So that was my little contribution was to use the Selbers sieve, and that will be the story for this one. So, okay, now we go real mathematics. This was done a bit later, and it's a problem which arises from computer science. and exactly from the so-called decimation problem. Now, everybody knows interpolation. If you have values of something, you try to get something in between which fits in a very regular fashion. Decimation is just the opposite. You have lots of data, and there are too many. So you want to decimate the data, remove as many as possible. So with just a little memory, you can describe some phenomenon or something. And this in computer science is very important. And there are many techniques to do that, and some of these techniques involve computer finite fields, and especially congruences modulo primes. Okay. So, okay. The origin of the paper in the distribution of powers, x to the k1, x to the k2, in small rectangular boxes. It's important for the application that the size of the box is a power of p strictly less than 1. So they're small boxes. However, also important that the powers k1, k2 are allowed to be large. Now, usually say, oh, just use Fourier analysis, and then you get the exponential sums, and this famous theorem of Weil, Riemann hypothesis in finite fields. Well, when the size, the exponent k goes above square root of p, you're lost. The Weil's theorem becomes essentially, in this situation, useless. So new techniques are needed. And a lot of Bourgain's work is related to find new techniques to handle this type of problems. And for example, a lot of his work on the sum product theorem in finite fields arose from the need of going beyond the application of Riemann hypothesis. So for the application to the decimation problem, the difference of exponents should be allowed to go as large as p. And then even the techniques of sum products and so on don't work anymore. So this took quite a while to figure out. And I will not go much in detail. Basically, the theorem, as you can see, gives the order of magnitude, the expected order of magnitude for the number of solutions of the congruence. The difference of the exponents is allowed to be p divided by constant. Certainly, constant 2 is not allowed. So that's more or less the best you can do. And however, notice that even if the number of solutions one would think should be this product n1 times nr over pr minus 1, which is so on average over boxes, there are some cases in which there are exceptional boxes with many more solutions of that. So that's interesting phenomenon, and go beyond that was proved to be very, very hard. My contribution was to work out the algebraic geometry needed because one needed to study some varieties which are some of monomials of a high degree, and then subvarieties, and then show these subvarieties can be stay in linear spaces involving only 2 variables. So that's required quite a bit of extra work. Another paper was this is a problem in which Bourgain was interested for a long time, and that is to study certain extremal property of polynomials, for example, with coefficient absolute value of 1, and what can you say about the minimal behavior on the unit circle. So unimodular polynomials, so coefficient absolute value 1, there was a conjecture Erdős that the maximum on the unit circle was strictly greater than square root n by positive constant c. This is one of the few conjectures of Erdős which turned out to be false. In 1966, Littlewood showed that you can get a bound square root of n except in a very small neighbor of 1 point where the polynomial is smaller. So that's what's called a flat polynomial, but the progress was done in 2 steps. One, showing that if you construct a polynomial with coefficient less than or equal to 1 in absolute value, there is a probabilistic procedure to make the coefficients the absolute value 1 without really changing the value of the polynomial. This is very simple. If you have the unit circle and the coefficient here inside, well, it's too short. What you do, you move in a perpendicular direction this way or that way at random. It goes to 1. But because you do randomly, the corrections cancel out. And so that's called the kernel correction. So here we studied various things. This is a sharpening of the Littlewood construction, in which the error is log n to the 3/2, and that is the same 3/2 we had got before in the first paper. And well, the interesting thing is there is a unimodular polynomial for which the absolute value on every point of the unit circle has an error term square root n, and the error term n to the half minus 1 over 9. A similar result, the same result with 1 over 17 was proved by Cahan, but using quite deep probabilistic construction. And fine, but we thought maybe we can do it in actual effective construction of that. And at first we did a little bit, then another little bit, and we worked 5 months on that, or in fact even more. I forgot how much, but I mean it became a personal challenge to do that. And eventually this was done using the Lynch theorem, the Riemann hypothesis for varieties in finite fields, but the varieties have the dimension which go into infinity. So this is the only situation in which I know that to prove one theorem for a specific thing, we needed to go all arbitrary dimension. So that was quite satisfactory, but I don't think people have read that paper because the proof of the effective construction goes for over 40 pages. Now, to say that the application of the Lynch theorem was not easy, and Nick has provided a solution using the elliptic Fourier transform and so on, and I mean very things. And eventually said maybe we can find some different way to show that we can apply the Lynch theorem. That took another month. Again, Bourgain made the first step, and then it was clear how to do the rest. And so we got it a little more elementary way, but very complicated. So that was, so let's see, next. Okay, and this will be the last one, very short. That's a problem which arises from a question in a model of mathematical physics. So distribution of nodal lengths of random Laplace eigenfunctions on the standard 2 torus divided by a lattice. So of course, they related the eigenfunction have a high multiplicity because they are correspond to the solution of the equation x squared plus y squared equal m. So that's the reason you can talk about random eigenfunction. If there are lots of solutions, you take a solution at random in that set, the number solution, the m's will have number solution going to infinity, and the question is, if you take one at random, what is how many, what is the nodal length, what is the variance, and so on. Now, to compute the variance, you have to compute essentially the 6th moment of the associated exponential sum. So that's a tough question, and that's the problem here at the bottom. So there are essentially, if you count, it's a plane curve in x and correspond to study plane curve. I'll show you why. So you fix the sum of x1 plus x2 plus x3, sum of y1 plus y2 plus y3, and then you have 6 unknowns and the equations and so on, and you get a curve degree 6 in the plane. And you want to study how many integral points on that curve. So that's not so easy. And at first I thought maybe this is the example of what happens with the solutions in the simplest case of 5 times 13, when m is that. And here this thing represents the, you see, you have these circles, but then you have to translate them because you have some of the 3 variables have to be a fixed number. And these are all the circles go around, there are these integral points, and then you translate and you look for common solutions. And this is is the simplest case. Now, Bourgain was in my office, was explaining that, oh, well, in a curve, I don't know the genus, if genus is 2, maybe you can, at least you can use Falting's theorem, and perhaps then if the genus is 1, well, I don't know, maybe then it's harder because you go to elliptic curves, and so it turns out Bourgain say, well, but is there anything else? Well, yeah, we see there's a circle, here's the point, then you have to make a translation, here's the other point. And he looks at Bombieri-Trotter theorem. And did a little calculation like that on the blackboard and say, oh, okay, the solution is the number of solution x squared plus x squared equal m to the power 7.5. Now, the fact is, n to the 4th is trivial, n cubed is conjectural, but little o n to the 4th is what the mathematical physicists wanted to know. So 7n to the 7.5 solves the problem at least. And then I said, oh yeah, you do this, that. I said, wait a moment. No, I don't understand how you do it because, you know, the curves here, there are that many, and here that many, the numbers don't fit. Then he looked at me and said, it's trivial. You have to look at level sets. So the interval in which you were looking, which goes from 1 to number d, let's say, you divide it in dyadic intervals. So the correction is given by a series like 1 plus 1/2 plus 1/4 plus 1/8. That's bounded. So just bounded the dyadic interval is what you do. And the computation goes in 2 pieces at the beginning and at the end. So you're optimizing it n to the 7/2. So we wrote that. I was not satisfied. Turns out you have elliptic curves. I will not tell you exactly how you do it, but you can linearize the system of curves. So they are degree 6 is a linear system, linear with dimension 1 on 9 base points. Fine. Those points are essentially generic position. Fine. So, but they are curves of genus 1. And because 9 points, there's a cubic curve through that. Counted twice. So this is a famous Helfen pencil of elliptic curves, which is the first example when you blow up the base points of a surface which is elliptic, because the fibers of genus 1 in general, and has a double fiber. That's a very special situation which occurs only in that case. So I started studying that, and eventually what came out, you have to take the Jacobian surface, so all the double fiber disappears, and suddenly it turns out this surface was studied by Bourgain and parameterizes a certain class of modular functions. And there are, according to torsion, I mean, I'm not going to go into details, but it's a very isolated object. There are, in fact, I think 6 of those Bourgain surfaces, and according to types of torsion. And it's a very interesting object. And then we still could not prove much but we proved that if the rank of elliptic curves is bounded, and now there's some evidence that it might be, then the n-cube conjecture may come out. And finally, it's this is an example of a sextic, the lines here, and the singular points are the double points, the 9 double points. So the next, Bourgain was not satisfied. So the result was let's look probabilistically. So you look first for square-free numbers, because that's really the interesting case. And Theorem 17 proves that indeed the bound is n cubed for almost all of them. And he was not satisfied, because the number of prime factors of a random number is not too large. But there are still lots of them have much more prime factors, and he wanted to study that. So we did this. And that took another couple of months. Let's see. So we ended up by proving the Riemann hypothesis for elliptic curves, Bourgain-Sweeten-Dyer conjecture, and then for square-free numbers, which have lots of prime factors, you get the bound and cubed. So this is what is known on the problem up to now without further conjectures. So this is the end of the 4 papers, or 5, 4.5. And the only thing I can say, it was always fantastic to work with Bourgain. And I will go to his office since at the time I was still single. And we start chatting and so on, and then we'll be late, we'll go out, eat something quickly, go back to the office, and at 3 o'clock at the night, I will say, well, it's time for me to go home. And this happened quite often. And it was always, there's one thing I want to show, but not go through that, but yeah. Let's see. How do remove that? Yep. Yeah, I have to remove that. Yeah. Oh, yeah. Yeah. Okay. Occasionally, for my own work, I will ask Bourgain, what do you think? And he will always think about it, maybe write 1 or 2 pages and send the pages to me. So this is an example of a little question about solving sum of xd d to the k for many k's. I want that to be controlled, to give it values in advance. And so here's an example, goes for 6 pages. It's quite application, very clever application of probabilistic methods, and is very, very good with that. I mean, it's fantastic, absolutely. And he thought about it, and after 3 days, sent me those things. Unfortunately, I've not been able to use this particular one, but it shows you how generous he is with his work, his thinking, and with people. Thank you.